Hello everyone, let's review the spring semester of the analysis module. First, let's define an open and closed disk. For a complex number and r a real number greater than 0, we define d of a and r to be the set of all z in the complex numbers such that the modulus of z minus a is less than r, and we define this to be the open disk with centre a and radius r. Similarly, for r greater than or equal to 0, we define d bar of a and r to be the set of all z in the complex numbers such that the modulus of z minus a is less than or equal to r, to be the closed disk with centre a and radius r. Now let's define open and closed sets of complex numbers. A subset S of complex numbers is called open if for any z in S there is a real number delta greater than 0 such that d of z of delta is a subset of S. A subset S of the complex numbers is closed if its complement, the complex numbers without S, is open. Next, let's define bounded and compact sets of complex numbers. A subset S of complex numbers is bounded if there exists a constant m in the real numbers such that the modulus of z is less than or equal to m for all z in S. A subset S of the complex numbers is compact if it is both closed and bounded. Now let's give a result for continuous functions. If f from the complex numbers to the complex numbers is a continuous function and capital F is a compact set in the complex numbers, then f of capital F, which is equal to the set of all f of z where z is in capital F, is also compact. A function f from the complex numbers to the complex numbers is continuous if and only if for every open set O, the set of the preimage of O is the set of all z in the complex numbers such that f of z is in O is open. If C is a compact set and Fn is a uniformly convergent sequence of continuous functions on C with limit f, then f is continuous on C. Now let's move on to defining a curve. A curve with parameter interval a to b is a continuous function gamma from a to b to the complex numbers, where a to b is an interval in the real numbers. We call gamma of a the initial point of gamma and gamma of b the final point of gamma. Hence, we get the following result. Let gamma be a curve with parameter interval a to b. Then the image of gamma, defined by gamma star is equal to the set of all gamma x where x is in a to b, is compact. Next, let's give some notation for curves. A curve gamma is said to be closed if its initial point and its final point are the same. So, if the domain of gamma is a to b, this means that gamma a is equal to gamma b. We say that gamma is simple if it is injective on a to b. So, gamma of s equaling gamma of t implies s equals t for any st in a to b. We say that gamma is smooth if it is differentiable and has continuous derivative. In other words, if the function gamma dash of t, which is the limit as t approaches t naught of gamma t minus gamma of t naught over t minus t naught, is defined for all t in a to b and is continuous on a to b. Given a curve gamma from a to b to the complex numbers, the inversion of gamma is denoted by minus gamma and is defined to be minus gamma of t is equal to gamma of b plus a minus t, so minus gamma is the same curve with opposite orientation. Given two curves, gamma 1 from a to b to the complex numbers and gamma 2 b to c to the complex numbers, such that gamma 1 of b is equal to gamma 2 of b, the join of gamma 1 and gamma 2 is the curve gamma 1 union gamma 2 defined on a to c by taking gamma t to be the value of gamma 1 of t if t is in a to b, and gamma 2 of t if t is in b to c. Next, let's define a path and a shape. A path is a curve which is the join of finitely many smooth curves. Given a path gamma, we also use gamma star to denote the image set of gamma. We will call the image set of paths shapes. In other words, a shape is a gamma star for some path gamma. Now, let's move on to parameterizing line segment. A line segment between a plus ib and c plus id is parameterized by gamma t is equal to a plus ib plus t minus s times c plus id minus a plus ib for t in s to r. Next, let's give the parameterization of circles. The circle centered at a plus ib with radius r is parameterized by gamma t equals a plus ib plus r times e to the it for t from 0 to 2 pi. Now, let's move on to define a contour. A circline path is a path which is the join of finitely many line segments and or circular arcs. A contour is a simple closed circline path. Next, let's define a region. A set S is said to be path connected if for every two distinct points z and w in S there is a path gamma such that the initial point of gamma is z, the final point is w, and the entire image gamma star of gamma is contained in S. An open path-connected set is called a region. Next, let's state the open mapping theorem. Suppose that S is a region and f is a holomorphic function on S. Then the image f of capital S is either a region or a point. Now, let's move on to giving results for piecewise continuous functions. Let a to b be a closed interval in the real numbers, and let h from a to b to the real numbers be a piecewise continuous function, i.e. h is continuous except possibly at a finite number of points a equals a0, which is less than a1, which is less than all the way up to an, which is equal to b. Then we define the integral from a to b of h of t dt to be the sum from k equals 0 to n minus 1 of the integral from ak to ak plus 1 of h of t dt. Now, let g from a to b to the complex numbers be a piecewise continuous function. As usual, we can write the function g of t to be the real part of g of t plus I times the imaginary part of g of t for t from a to b. Then, we define the complex integral, the integral from a to b of g of t dt, to be the integral from a to b of the real part of g of t dt plus I times the integral from a to b of the imaginary part of g of t dt. Next, we have the linearity property, i.e. for f and g piecewise continuous functions on a to b and lambda and mu in the complex numbers, the integral from a to b of lambda times f plus mu times g of t dt is equal to lambda times the integral from a to b of f of t dt plus mu times the integral from a to b gt dt. Then we have the additivity property, i.e. for f from a to b to the complex numbers and a less than c less than b, the integral from a to b of f of t dt is equal to the integral from a to c of f of t dt plus the integral from c to b of f of t dt. Also, we have that the integral from a to b of f of t dt is equal to minus the integral from b to a of f of t dt. Also, we have the substitution property, i.e. if phi from a to b to c to d is differentiable and f from c to d to the complex numbers, then the integral from c to d of f of s ds is equal to the integral from a to b of f of phi of t times phi dash of t dt. Next, we have the estimation property, i.e. if f from a to b to the complex numbers, then the modulus of the integral from a to b of f of t dt is less than or equal to the integral of the modulus of f of t dt. Now, let's move on to defining integration along a path. Let gamma from a to b to the complex numbers be a path, and let a equal a0, which is less than a1, all the way up to an, which is equal to b, such that y restricted to ak plus 1 is smooth for k between 0 and n minus 1. Let f from gamma star to the complex numbers be continuous, so that f circ gamma times gamma dash from a to b to the complex numbers is a piecewise continuous function and hence integrable. Then we define the integral over gamma of f of z dz to be the integral from a to b of f of gamma of t times gamma dash of t dt. Next, let's give some results for integration along a path. Suppose that gamma from a to b to the complex numbers is a path, and that f and g from gamma star to the complex numbers are continuous, and that lambda and mu are complex numbers. We have the linearity property that the integral over gamma of lambda f plus mu g of z dz is equal to lambda times the integral from gamma of f of z dz plus mu times the integral over gamma of g of z dz. We also have the inversion property that the integral over minus gamma of f of z dz is equal to minus the integral over gamma of f of z dz. We also have the additivity property that if a is less than c, which is less than b, and we put gamma 1 to be gamma restricted to a to c and gamma 2 to be gamma restricted to c to b, then the integral over gamma of f of z dz is equal to the integral over gamma 1 of f of z dz plus the integral over gamma 2 of f of z dz. Further, we have the reparameterization property, which says that if psi from a tilde to b tilde to a to b is a continuously differentiable bijection, and that gamma tilde is equal to gamma circ psi, then the integral over gamma tilde of f of z dz is equal to the integral over gamma of f of z dz. We also have the fundamental estimate property, which says that if gamma from a to b to the complex numbers is a path, and that f from gamma star to the complex numbers is continuous, then the modulus of the integral over gamma of f of z dz is less than or equal to the integral from a to b of the modulus of f of gamma of t times the modulus of gamma dash of t dt. Hence, putting m equal to the supremum over all z in gamma star of the modulus of f of z, and L to be the integral from a to b of the modulus of gamma dash of t dt, which is the length of gamma, then the integral over gamma of f of z dz is less than or equal to ml. Next, let's give the fundamental theorem of calculus. Suppose that gamma from a to b to the complex numbers is a path, that capital F is a holomorphic function on an open set containing gamma star, and that f dash of z is continuous at each point of gamma star. Then the integral over gamma of f dash of z is equal to f of gamma of b minus f of gamma of a. Next, let's give some results for the fundamental theorem of calculus. If gamma from a to b to the complex numbers is a closed path, f is a holomorphic function on an open set containing gamma star, and f dash of z is continuous at each point of gamma star, then the integral over gamma of f dash of z dz is equal to 0. Also, if we are given a function f which is continuous on the image of some closed path gamma, and the integral over gamma of f of z dz does not equal 0, then, by the fundamental theorem of calculus, there can be no holomorphic function f on gamma star such that f dash is equal to f. Next, let's discuss how uniform convergence and integration relates. Let gamma from a to b to the complex numbers be a path, and for n from 1, 2, 3, etc., let fn from gamma star to complex numbers be a continuous function. Suppose that fn converges uniformly to f from gamma star to the complex numbers on gamma star. Then the limit as n approaches infinity of the integral over gamma of f of n dz is equal to the integral over gamma of f of z dz. Then let's discuss how infinite series and integration relate. Where we can apply the Weierstrass M test, we can exchange the order of integrals and infinite series to get that the integral over gamma of the sum from k equals 0 to infinity of uk of z dz is equal to the sum from k equals 0 to infinity of the integral over gamma of uk of z dz. Now let's move on to Goursat's lemma. Suppose that f is holomorphic inside and on a triangular path gamma. Then the integral over gamma of f of z dz is equal to 0. Next, let's state an application of Goursat's lemma. For n greater than or equal to 0, let Sn be a compact subset of the complex numbers, with Sn plus 1 being a subset of Sn. Then the intersection from n equals 0 to infinity of Sn does not equal the empty set. Next, let's state the antiderivative theorem. Let S be a convex region, and let f from S to the complex numbers be a holomorphic function. Then there exists a holomorphic function capital F from S to the complex numbers such that capital F dash is equal to f. Then let's give an application of the antiderivative theorem. Let S be a convex region, let f from S to the complex numbers be a holomorphic function, and let gamma be a closed path in S. Then the integral over gamma of f of z dz is equal to 0. Now we can state Cauchy's theorem. Suppose f is a function which is holomorphic on and inside a simple closed path gamma. Then the integral over gamma of f of z dz is equal to 0. We can also describe Cauchy's theorem in another way. Suppose gamma 1 and gamma 2 are simple paths with the same initial and final points and with no intersection. Suppose f is holomorphic on gamma 1 star and gamma 2 star and between them. Then the integral over gamma 1 of f of z dz is equal to the integral over gamma 2 of f of z dz. This follows from Cauchy's theorem by considering the simple closed path which is the join of gamma 1 and minus gamma 2. Next, let's state the covering theorem. It says we can cover gamma star by a finite number of open disks d1 to dn contained in S such that di intersect di plus 1 intersect gamma star does not equal the empty set for all I less than capital N, and d capital N intersect d1 intersect gamma star does not equal the empty set. Now let's define a positively oriented path. A simple closed path gamma is positively oriented if, as t increases, gamma t ends up moving anti-clockwise around any point inside gamma. Next, let's define the deformation theorem. Suppose gamma 1 and gamma 2 are positively oriented simple closed path and gamma 2 star is inside gamma 1 star. Suppose f is holomorphic on gamma 1 and gamma 2 and between them. Then the integral over gamma 1 of f of z dz is equal to the integral over gamma 2 of f of z dz. Now we can move on to stating Cauchy's integral formulae. Let gamma be a positively oriented simple closed path, and let f be a function which is holomorphic in and inside gamma star. Suppose a is inside gamma star. Then f of a is equal to 1 over 2 pi I times the integral over gamma of f of z divided by z minus a dz. And for n equals 1, 2, etc., the nth derivative of f at a exists, and the nth derivative of n at a is equal to n factorial over 2 pi I times the integral over gamma of f of z divided by z minus a to the n plus 1 dz. Hence, we have the following result. Suppose f is holomorphic in an open set S. Then f has derivatives of all orders in S. Now, we can state Taylor's theorem. Suppose a function f is holomorphic in an open disk D of a and r. Then there exists a constant Cn in the complex numbers such that f of z is equal to the sum from n equals 0 to infinity of Cn times z minus a to the n for all z in the disk of a and r. Moreover, for any r between 0 and r, we have that Cn is equal to 1 over 2 pi I times the integral over gamma of a and r of f of w divided by w minus a of m plus 1 dw, which is equal to the nth derivative of f at a divided by n factorial. We can now give an application of Taylor's theorem, which is Liouville's theorem. Suppose f is holomorphic in the complex numbers and bounded, that is, there is an m in the reals such that the modulus of f of z is less than or equal to m for all z in the complex numbers. Then f is constant. We can now state an application of Liouville's theorem, which is the fundamental theorem of algebra. Suppose p of z is a non-constant polynomial with coefficients in the complex numbers. Then there is a Cauchy in the complex numbers such that p of Cauchy is equal to 0. So any polynomial with coefficients in the complex numbers has a root in the complex numbers. And so p of z equaling z to the n plus a n minus 1 z to the n minus 1 all the way up to a naught is equal to z minus Cauchy 1 times all the way up to z minus Cauchy n for some Cauchy 1 to Cauchy n in the complex numbers. Now, let's define the zeros of holomorphic functions. Suppose f is holomorphic in D of a and r. Then a is a zero of f if f of a is equal to 0. And a is an isolated zero of f if f of a is equal to 0, and there exists an epsilon greater than 0, such that d dash of a and epsilon contains no zeros of f. So, a zero of f is isolated if and only if it is not a limit point of zeros of f. Hence, we have the identity theorem. Suppose S is a region and f from S to the complex numbers is holomorphic. Let capital Z of f be the set of all zeros of f in S. If capital Z of f has a limit point in S, then f is identically equal to 0 in S. So, in the situation of the theorem, if f is not a zero function, then all the zeros of f in S are isolated. Hence, we have the uniqueness theorem. Suppose S is a region and f and g from S to the complex numbers are holomorphic. Let I of f and g be the set of all z in S such that f of z is equal to g of z. If I of f and g has a limit point in S, then f is identically equal to g in S. Now let's move on to defining the Laurent expansion. Let 0 be less than or equal to r, which is less than r, which is less than or equal to infinity, and let a be the set of all z in the complex numbers such that the modulus of z minus a is between r and r, which we call an annulus with centre a. Let f from a to the complex numbers be a holomorphic function. Then f has an expansion f of z is equal to the sum from n equals minus infinity to positive infinity of Cn times z minus a to the n for z in a, where Cn is equal to 1 over 2 pi I times integral over gamma of f of w divided by w minus a to the n plus 1 dw, with gamma equal to gamma of a of s for any S between R and R. This expansion is called the Laurent expansion. Now, let's move on to give some notation for singularities. Let f be a complex function. The point A, a complex number, is a regular point of f if f is holomorphic at A. The point A, a complex number, is a singularity of f if it is not a regular point, but it is a limit of points of regular points. A singularity A of f is called an isolated singularity if f is holomorphic in some punctured disk d dash of a and r. It is a non-isolated essential singularity otherwise. Next, let's give some classification of isolated singularities. Suppose A is an isolated singularity of f. So f has a unique Laurent expansion f of z is equal to the series from n equals minus infinity to positive infinity of Cn times z minus a to the n for some z in the punctured disk d' of A and R. The point A is called a removable singularity if Cn equals 0 for all n less than 0, so that f of z is equal to the series from n equals 0 to infinity of Cn times z minus a to the n. The point A is a pole of order m, where m is greater than or equal to 1 if C of minus m is not equal to 0, but Cn equals 0 for all n less than minus m, so that f of z is equal to the series from n equals minus m to infinity of Cn times z minus a to the n. The point A is an isolated essential singularity otherwise. The poles of order 1, 2, 3, etc. are called simple poles, double poles, triple poles, etc. Now, let's give the results for poles and zeros. Suppose that f is holomorphic in an open disk D of A and R, and f of A is equal to 0, but f is not identically equal to 0 in the disk of A and R. Then, f has a Taylor expansion f of z is equal to the sum from n equals m to infinity of Cn times z minus a to the n for z in the disk centered A radius r, for some integer m greater than or equal to 1 with Cm not equal to 0. In this case, we say that f has order m at A. Note that f has a 0 of order m at A if and only if we can write f of z is equal to z minus a to the m times g of z for z in the disk centered A radius r, where g is a function holomorphic in the disk center A radius r, for which g of a does not equal 0. In terms of the Taylor expansion, the function g is given by g of z is equal to the sum from n equals 0 to infinity of c sub n plus m times z minus a to the n for z in the disk center A radius r. Since we have the formula Cn is equal to the nth derivative of f at A divided by n factorial for the coefficients of the Taylor expansion, we have that f has a 0 of order m at A if and only if f of a equals f dash of a equals all the way up to the m minus 1th derivative of a equals 0, and the mth derivative of f at a does not equal 0. Now, let's describe the relation between zeros and poles. Suppose f is holomorphic in some open disk D centered at A with radius r. Then f has a 0 of order m at A if and only if 1 over f has a pole of order m at A. Now, let's describe how the product of functions relates to poles and zeros. Suppose f has a pole of order m at A. If g is holomorphic in a disk centered A radius r, then the function fg has a pole of order m at A if g of a does not equal 0, a pole of order m minus n at A if g has a 0 at A of order n less than m, a removable singularity at A if g has a 0 at A of order n greater than or equal to m. If g has a pole of order n at A, then fg has a pole of order m plus a at g. Next, let's describe how the quotient of functions relates to poles and zeros. Suppose f and g are holomorphic in an open disk centered at A radius r, and g has a 0 of order m at A. Then the function f divided by g has a pole of order m at A if f of a does not equal 0, a pole of order m minus m at A if f has a 0 at A of order n less than m, a removable singularity at A if f has a 0 at A of order n greater than or equal to m. Now we can state the Casorati-Weierstrass Theorem. Suppose f has essential singularity at A. Let w be any complex number. Then there is a sequence of complex numbers an converging to A such that f of an converges to w. Next, we can state Picard's theorem. Suppose f has essential singularity at A. Then there exists w0 in the complex numbers such that for all epsilon greater than 0 and w in the complex numbers without w0, there is a z in the punctured disk centered A radius epsilon with f of z equal to w. So, in any punctured disk around A, the function takes all but at most one value of the complex numbers. Now, let's move on to state Cauchy's residue theorem. Suppose f is holomorphic on and inside a positively oriented simple closed path gamma, except for a finite number of poles at a1 all the way up to am inside gamma. Then the integral over gamma of f of z dz is equal to 2 pi I times the sum from k equals 1 to m of the residue of f of z at ak. Hence, we have the following result. Suppose f has a simple pole at a, then the residue of f of z at a is equal to the limit as z approaches a of z minus a times f of z. And, as ever, thank you for watching.